Part 4. Instrumental colour measurement. The purpose of colour measurement technology is to give you access to an objective evaluation of colour. Colour measurement instrument will control the illuminant and the observer. Standardisation and traceable calibration makes this data globally consistent. To be able to properly interpret and reproduce colour data values, you need to know the geometry of the measuring instrument. A measurement geometry is described by two values, the angle of illumination and the angle of observation. Both angles are calculated relative to the normal of the sample. Different industries and applications may prescribe different geometries. There are two dominant geometries used in colour measurement. The first is 45-0, which means that the sample is illuminated at a 45-degree angle, while the sensor is positioned exactly perpendicular to the surface area. This geometry corresponds well to how samples are visually assessed. Instruments with 45-degree geometry are often used in the printing industry, for car interiors, and the measurement of high visibility clothing. One important property of the 45-0 geometry is that the measured value will strongly depend on the glossiness of the sample. The more glossy, the more light will be reflected away from the sensor. This will cause you to measure a darker colour of a glossy finished material compared to a matte finished material. The second commonly used geometry is diffuse 8. This indicates a diffuse illumination and a sensor that is positioned at 8 degrees from the normal. A sample is diffusely illuminated if light is coming evenly from all directions. This can be achieved not by illuminating the sample directly, but by illuminating a white sphere instead, which is positioned on top of the sample. The light is scattered across the surface of the sphere, resulting in illumination from all angles. In general, a larger sphere will provide you with more accurate colour values. The advantage of a diffuse illumination is that the measured value is now independent of the surface finish, so you're really measuring the colour of the material and not how it is perceived. Nevertheless, most diffuse 8 instruments will also allow you to take a measurement excluding the specular reflection, and therefore provide you with a value that better corresponds to the visual impression of the colour. This is done by including a small trap into the sphere that can be opened and closed. As this trap is also positioned at 8 degrees from the normal, but opposite of the sensor, all of the specular reflection is removed when the trap is opened. This is called SCE mode, or specular component excluded. When the trap is closed, you're measuring in SCI mode, or specular component included. The way that colour measuring instruments capture the reflected light also leads to two different implementations. Tristimulus colorimeters, such as Konica Minolta's chromometers, utilise red, green and blue colour filters that correlate with the human eye. The reflected light received through the filters is the colour that a human observer would perceive the object through the red, green and blue sensitive cone cells of the human eye. Behind each of the filters is a dedicated sensor capturing the amount of light passing through. So, internally a colorimeter will have 3 different signals for a single measurement, one for the amount of red light, one for green and one for blue. Spectrophotometers utilise a diffraction grating to separate the light instead of filters. A diffraction grating is an optical element which acts similarly to a prism. It separates the reflected light from the sample into evenly sized portions of the visible spectrum. So, instead of just 3 sensors, spectrophotometers have 30 or more sensors covering the entirety of the visible spectrum. This makes a more detailed and often more useful device than a colorimeter. In particular, a spectrophotometer will provide you with the option to predict how a colour will look under different light sources. 2 or more samples that match under one light source but do not match under a different light source are said to be metameric. Sometimes the effect can be quite extreme. and this poses a big problem for producers. Imagine that you purchase a brown sofa, but when you get it home, the base of the sofa is still brown, but the cushions now look green. The following example can help explain this phenomenon. Specimen A is purple. On the left, you can see the two observation illuminants D65 and illuminant A. To the right of the illuminant data, you can see LAB values under each illuminant, and to the right, the spectral reflectance curve of the sample. When we introduce specimen B, it's a good match to specimen A under D65, with a delta E value of 0. However, under illuminant A, the specimens appear very different indeed, with a large colour difference of more than 8 delta E. It's not only when mixing samples matched with different pigments that the interaction between colourants and illuminants can be a challenge. Even if the entire sofa used the same dyes as specimen B, the colour is inconstant. It changes its appearance greatly dependent on the lighting, and typically producers also like to avoid this effect. When you go about selecting a colour measuring device, a representative from Konica Minolta Sensing can advise you on the relative merits of the various technologies, geometries, and measurement conditions specific to your samples and